Welcome to Mastering Solutions. We need to use an equation from our diffraction grating equation list that has theta in it because, of course, we're looking for the angle of the first two diffraction orders. So the equation that we'll be using is sine of theta is equal to m lambda over d. Now, it's not solved for lambda, but we can pretty easily do that by just taking the inverse sine of both sides of the equation. So the equation will be sine is equal to inverse sine times m lambda over d. And the equation right here, this is appropriate for m equals 0, 1, 2, 3, etc. So it has to be a whole integer. And they want to know the first two diffraction orders. So we're going to be using m is 1 and m is 2. So to do that, let's take m1. And we need to plug in the information, but we don't know what d is. So we know that the wavelength is 550 nanometers. So lambda is 550 times 10 to the negative 9 meters. And we know that m for this one is going to be m equals 1, of course. And for d, we need to figure that out. It's not given. So for d, remember that it's always going to be the width of the diffraction grating divided by the slits. As I've said in some of the other videos, a lot of times students will get this confused and they'll flip it, but this is how you find d. So in this case, we have 1 centimeter. So that's going to be 1 times 10 to the negative 2 meters divided by the slits, of course, is 1,000. So we have 1e negative 2 divided by 1,000, and that's going to be 0.00001. And if we plug it into psi mode, we have 1 times 10 to the negative 5, and that is, okay, so there we go. Now, we don't have to calculate it. You could just plug this in. That's what I usually like to do, just to, so I avoid a error, but this is pretty easy to copy forward, of course. So for m1, we have inverse sine, and m is 1. Lambda is 550 times 10 to the negative 9 meters, and that's divided by 1 times 10 to the negative 2 meters over 1,000. And as we just talked about, you can just plug that straight in if you want, either way. And so we have inverse sine of 1 times 550 times 10 to the negative 9. And then that's divided by 1 times 10 to the negative 2 divided by 1,000. And that gives us 3.15, and we are in degree mode. So I'm going to switch this over into radians just for practice. So we have, let's go into normal again. Okay, so we have 0.055. So the answer for this in radians is 0.055 radians. Now, they want to know what the angles are, so we need to convert that into degrees. We already found it, of course, when we had our calculator in degree mode, but just for practice, we should convert this into degrees the other way as well. So we have 0.055 radians, and to convert from radians, we're going to have pi radians is 180 degrees. So we have our answer times 180 divided by pi, and that gives us 3.15 degrees, which of course we already found. So 3.15 degrees is our answer for how many degrees the first angle for the first diffraction order. Now let's do the same thing for m of 2. So we have inverse sine of 2 times 550 nanometers, and that's all over 1 times 10 to the negative 2 meters or centimeters divided by 1,000. And for the calculator, of course, we can just take that and then just change to 2. There we go. M is 2. And so that gives us in radians is 0.11 rad. So 0.11 radians. And then if we convert that to degrees, we're going to have our answer times 180 divided by pi. There we go. Okay, so for degrees, we have 6.32. So that is 6.32 degrees. And so that is your answer for the first two diffraction orders. We have 3.15 and 6.32 degrees.